So, I welcome everyone. Thank you very much for joining us. I'm sure some of our colleagues will be joining gradually during the talk. Today we have Yani Najman from Lancaster University. She'll be talking about the evolution of the Indus River drainage and its influence on the Indus Fan sediment archive. Bob obviously will be discussing about the future speakers, and I think we just discussed that we are nearing to the first or this current session. We might have two more speakers. I'm not quite sure. And there was a very good idea which came from Bob that he'll be, presenting a sort of synopsis of all 20 talks that we obviously participated. So I'm not taking more of your time. I'm just inviting Bob to introduce Yani in details and also discuss about the future presenters if there are any confirmation. Bob, over to you.
Thank you very much, Irfan, and thank you, Mukhtar, for coordinating out of Quetta and the GSP office. And we're really, this seminar has come together because of the work of so many people, and especially the help from the Geological Survey of Pakistan in their Quetta office. And Mukhtar, we're awfully grateful for your continued work over many weeks. This evening, or this morning, we have a lecture which I think is approximately number 20 in the series. And I just want to give a quick view into the future. Next week, we've got Advait Junkhar, who's currently at Yale University. He's going to be speaking about paleontology in the upper Siwaliks. And I've spoken to him at great length about the elephant fossils and the mammoth fossils. So he'll certainly be talking about the fossil proboscideans from the Siwaliks. The following, anticipating being the final of this series of the seminar. And we may have Dr. Imran Khan from the GSP with us that evening. And I'm planning to give a synopsis of the 20 lectures, really sort of to revisit what we've heard over the last several months. And it'll be a great pleasure for me to review it. And it's been mentioned that we should comment on a little bit about the numbers of people and the different countries and things that have been involved, because this has been a wonderful international collaboration. It's been a great pleasure. And we'll also be maybe talking a little bit about, do we want to start up again in the fall? And we'll be looking for suggestions from the audience about what future directions might be useful. But this evening, it's of course our great pleasure to welcome Yani Najman, who is joining us actually, and she's a professor at the university at Lancaster University in the United Kingdom, but she's currently located in the Rocky Mountains just west of where I live, in a beautiful little town called Nederland, that is a famous ski town, and it's famous for sort of a mountain lifestyle. So I'm picturing Yani is living up in the mountains and somehow managing to teach her classes on tectonics and sedimentation at Lancaster University. It's a wonderful thought. And Yani is educated in Edinburgh. She got her PhD from Edinburgh University in the United Kingdom, but she's worked across the entire span of the Himalayas. So you'll hear tonight some of her discussions, but she's worked in Pakistan, she's worked in India, she's worked in Nepal, she's worked across into Tibet and all the way across into Myanmar. So she's got a wonderful background in the geography and in the geology of the Himalayas, and she's interested keenly in the interrelationships between tectonics and sedimentation. So I'm going to turn it over to Yani here in a second. And just to note that if any of you have questions or if anything comes up, we'll plan to have an opportunity at the end of the series, at the end of the talk today, to answer any questions you might have. So Yani, we welcome you to the seminar.
Thank you very much, and thank you very much for inviting me. So let me share screen, and then hopefully I can start. Share content.
Yeah.
So am I on
It's
full
nice
screen now?
It's still display mode. There you go.
Yeah,
That's good.
that's fine.
Okay. So yeah, thank you very much for inviting me to talk at this seminar series. Bob asked if I could briefly introduce myself and my motivations for working in these beautiful mountains. I guess I've always loved mountains ever since I was a little girl, and I grew up in London in the UK, so obviously I didn't see any mountains. And then the first time I saw them was I was about 12 or 14 years old, and I just thought that these were just little mountains in Wales in Great Britain, and I just thought they're just so beautiful. And so kind of from then on, that was, I wanted to study them. And then I thought, well, which are the biggest? I thought, well, the Himalayas. And by then I was 17 or 18 and I'd started traveling, and traveling is one of my main passions in life. So what better way to combine my work with my love of traveling? And not only have I seen beautiful scenery, but I've been able to take part and enjoy beautiful cultures and meet with many different people, right the way through from Pakistan in the west through to Myanmar in the east. And yeah, it's been a real privilege. So moving on to a little bit more about the science. What I'm going to talk about today is the evolution of the Indus River drainage and its influence on the Indus Fan sediment archive. So the reason I'm interested in sedimentary archives is that they're used to determine hinterland tectonics. So obviously you can go to a mountain belt and you can analyze the bedrock, and that will give you lots of information about how the mountain belt was formed. But a lot of the early history of that mountain belt isn't preserved in the mountain belt itself anymore, because it's been removed by erosion, or it's been overprinted by metamorphism, or there's been tectonics. So in that case, the only remaining record can sometimes be the material that's been eroded and then deposited in the adjacent basins. So those are the sedimentary archives that I mean. But in order to be able to interpret these sedimentary archives properly, we need to know their autogenic and their allogenic influences. So the Indus Fan, which is what I'm going to be focusing on today, here we can see it. It's the second largest submarine fan in the world, the biggest one being over here, the Bengal Fan, also draining the Himalayas. So the Indus Fan is fed by the Indus River, which drains the Western Himalaya and south of Tibet. And there's also some influence from peninsular India, but it's predominantly a record of the Cenozoic collision of India and Asia and the subsequent orogenic evolution. So the sediment archive that we have here, obviously it's deep in the oceans, so unlike the Fallen Basin, which is more of my normal stomping ground, here we can't just get a hammer and go out and whack it. We have to go on a boat and drill it. So IODP Expedition 355 in 2015 went to the Indus Fan. That was led by co-chiefs Peter Clift and Pandy. I actually wasn't on that one. I was going to go on this one, but I was going to apply for it. But the one to the Bengal Fan was the one just before it, and I got accepted on that. So that was the one I took. So I don't think you can apply for two. And also my university might want me back at some point. So I went on the first one that I was accepted on. There's also some older samples from ODP and DSDP, but they've got fairly limited samples. These samples here are also fairly limited. It did drill to Cretaceous basement, but there was only about 11 million years of the Indus Fan, because below that they hit a mass transport complex. And then there was a tiny bit of Indus Fan below that, about 15 million years of 15 million year sample or so. But it doesn't go back that far. And then there's also, I believe it's a German industrial well, Indus Marine A1, which goes back to, I think, about 15 million years. So then if we look at the Indus River that feeds the Fan, here we've got it on the topography. And what's important to note is that the Indus comes all the way back to the north and then drains along the suture zone. And that's in comparison to what we call the Punjab tributaries, which only drain the Indian plate. So if we take that and we show it on the geological map, here in orange, we've got the River Indus, and you can see it drains back through the Indian plate, then into the suture zone, and then along the suture zone and the Kohistan-Ladakh island arc. And by contrast, these purple rivers, the Punjab tributaries, only drain the Indian plate. And that means there's a different provenance between the Indus and the Punjab tributaries, in that the Indus versus the Punjab only draining the Indian plate. So, for example, all the zircons, the UPB ages, will be old because the Indian plate is old. And by contrast, the Indus, although it drains the Indian plate, because it also drains the arc and suture zone, and the arc is Cretaceous to Paleogene aged, will also get additional zircons, which are Cretaceous to Paleogene aged, and will get more geochemical influence and petrographic influence of the arc. So that's the important point to note, and it's the big point of how I can make the conclusions that I'll come to, is that we have a different provenance between the Indus and the Punjab territories, in that we have Cretaceous to Paleogene arc material in the Indus. So there's major debates as to when the river began. We've got Clift et al., Sinclair and Jaffe, Henderson, myself, Bhattacharya. And these discussions relate to really when the Indus started flowing along the suture zone. And estimates range from Eocene, which is Peter Clift, right the way through to Miocene, which is Sinclair and Jaffe. But that's not what I'm going to be focusing on today. I'm going to be focusing on this downstream area. So Clifton, I'm probably not going to pronounce this correctly, but I'd like to, Blustein, in Nature 2005, they looked at epsilon nidinium ratios. This is epsilon nidinium of the Indus Fan. They drilled through the Indus, well, they got samples that have drilled through the Indus Fan all the way from, say, 30 to present day, and this is the modern Indus River. And they looked at their epsilon nidinium values. And epsilon nidinium tells you how much Himalayan material there is. So values of the Indian plate are more negative, whereas suture zone and arc is more positive. It never actually, well, if you were at the arc yourself, it would become positive. Okay, so more positive values, suture zone and arc, more negative, Indian plate, Himalaya. And what they saw was quite a big change around about 5 million years, where you get a lot more negative. The values become a lot more negative. And how they interpreted this was that compared to the present day scenario, they maintained prior to the time of change, these Punjab tributaries actually drained to the east, and they went to the Bengal Fan. And then at the time that they started draining to the west, that's when you're going to get an awful lot more Indian plate material coming in. And so that drove the signal right the way to the more negative side. So that was their view. But then Charouz et al. In Journal of Geology 2015, They said, no, that change is not due to a major drainage reorganization. They thought that there'd been a stable drainage since the mid-Miocene at least, and that you've had variable exhumation of the source regions that have caused this change. And the reason they thought this is that here we have the Indus Fan data again. This is the ages of the drill samples. And then coming through to the modern day. So here you can see that change again. And they compared that change with fallen basin samples of about 12 million years and modern data from the range front, so kind of in the fallen basin. And they noticed that from the start of their studied record of mid-Miocene to present day, you've always got about a 4 epsilon neodymium value difference, about 4 units different between here and then again up here. So they're saying it's remained stable, and both the upstream and the downstream have changed due to changes in the exhumation of the source region. And they also did zircon fission track, so the time that the zircon mineral cooled through the fission track closure temperature. And they noticed that there was a decrease in the old ages and the old lag times up section. And they thought that this represented a change between the relative inputs of the Kohistan Island arc versus Indian plate and Karakoram. So the aim of this research was to differentiate between the two hypotheses, because if you have the geochemical change at 5 MA, if it was due to the Punjab tributaries joining the Indus drainage, then what you should see is that before the drainage reorganization, i.e. when these rivers were going the other way, the upstream in the peripheral fallen basin and the downstream below the confluence should look similar. But after the Punjab tributaries have joined the confluence, then the downstream signature, downstream of the confluence, should increase in the proportion of Indian plate material relative to the upstream, but the upstream should remain the same. So that was what we were looking for. We're looking to compare the upstream and the downstream and see if this hypothesis held true. We were using existing proxies, strontium neodymium composition of bulk rock, but we also added new proxies. We did uranium lead dating on detrital zircons, and we wanted to complement the strontium neodymium, because strontium neodymium is a bulk rock technique that, as I showed you, tells you how much arc up here versus Indian plate material there is, and Karakoram. But uranium lead dating of detrital zircons will do the same thing, because the Indian plate has old grains, the arc has Cretaceous and Paleogene grains, and the Karakoram has a bit of both. We also wanted to take on argon-argon of detrital micas because they have a similar closure temperature to zircon fission track. So we wanted to compare our data with that of Charouz et al. Using a different technique. And as well as using existing and new proxies, we also wanted to extend the record back in time to the start of the continental fallen basin record. So yeah, before I carry on, just to briefly go through the geology here, this is the peripheral fallen basin, or the sub-Himalaya. So we got samples from here, and we compared them with the Suleiman and Kirta ranges down here. Then in green and blue, we have the Indian plate. Then we have the Kohistan Ladakh Island arc, and then we have the Asian plate of the Karakoram to the north. So we've got the Suleiman and the Kirta downstream comparison here. This is going to be based on published data that we're making this comparison. So in the peripheral fallen basin and the Hazara Kashmir syntaxis, we have the Kuldana formation. This is the transitional to continental facies, which is in the Eocene. Then we've got a really annoying unconformity, so we don't have any data between those times. And then we go from the Murray, which is early Miocene, then the Cambrial, and then Chinji, Nagri, and Dokparthan, which are the Siwaliks, and they're dated by magnetostratigraphy. That's Johnson et al., I think 1985. And then the lower Indus Basin, the Suleiman and Kirta, we have various different formations, and there's no unconformity there, or no big one, so we get a more complete record. And the data that we're comparing with here are from Rodaz et al. 2011 and Zhuang et al. 2018. No, 2018? Yes, that's actually one of the papers that I was involved with. So first of all, before we got started, we wanted to make sure that we wanted to confirm that we really did see this geochemical change in the Indus Fan. So this is, by this time, Clift et al. Had got more data. So this is the 2019. You can see they've now got more data points. You still do see this pull towards more negative epsilon neodymiums, round about, well, 5 million years maybe. These more positive values, the paper considers them to be due to Deccan trap input contaminating or influencing the results. And here you can see the same thing with the Deccan trap pulled out. So we did mixture modeling on these samples, and we did not use the samples that Clift et al. Were concerned had Deccan trap contamination. And you can see really nicely, we've got the different age groups of the samples, 15 to 10, 10 to 8, 8 to 6, 6 to 3, and 3 to 0 MA. And you can see this really nice change between around about 6 million years, where we don't have any more, we don't have any blue 8 to 6 MA samples any more negative than about 10.5 or 11, minus 10.5 or minus 11. So that confirms that what the change that Clift et al. Thought they saw also holds up when you actually do mixture modeling, bringing in the strontium. Well, I should say as well, the end point, the end member up here is the Kohistan Ladakh Island Arc. We have the Tethyan Himalaya end member here, the Karakoram end member here. Lesser Himalaya goes off way over here, and the Greater Himalaya is another end member over here. And then we did the mixture modeling with the samples for the Deccan trap excluded. So then moving on from the Indus Fan to our new data from the Foreland Basin and comparing it with the downstream. So from the Foreland Basin, we have in green, and we can see we have the Eocene here. We've got the ages of the samples up here, and epsilon neodymium, Himalaya over here, suture zone over here. In the Eocene, Kuldana Formation, we have values about -8, -9. Then, because of the unconformity in the Foreland Basin, we don't have any data. And then we come up into the Murray and then the Siwaliks. And we can see that in the Foreland Basin, there's very little change up section, except for this Murray Formation sample in red. This is the Murray Formation sample at Murray Hill Station. Murray Formation at other localities, like in the Hazara Kashmir syntaxis, behaves normally. So I'm going to talk about the Murray Formation at Murray Hill Station separately. But overall, you can see there's not much change. And also you can see that the downstream, below the confluence over here, is the same as the upstream in Eocene times, but by the Oligocene, it started to pull towards more negative values of the Himalayas, and it stays more negative than the upstream, except for in the Nagri Formation here. And this is I should have said, is black. The black samples are the axial Indus Basin. So from this, we interpret that the Punjab tributaries joined the Indus drainage early between the Eocene times, when the upstream and the downstream were the same, and then you're starting to get this pull in the Oligocene towards more negative values, which could be interpreted as the Punjab tributaries coming in. As well as using epsilon-Neodymium, we also did the mixture modelling. This just shows the end members. So we've got the suture zone and the Kohistan Ladakh Island Arc up here as an end member. We've got the Karakoram, Tethyan Himalaya. We put the Lhasa block in as well, just to see what would happen. Greater Himalaya and the Lesser Himalaya, with these are the end members, the typical signatures of these units. And what we see is that when we then superimpose on these end member values, we superimpose the values from the fallen basin, that's in black. So these black dots here. So apart from the Marie Formation at Marie Hill Station, which again is out by itself, there's not much change overall through time in the fallen basin. And then if we compare it to the downstream, the Eocene is quite like the fallen basin, but by the time you head to the Oligocene, we've got a change. These are more negative, more Lesser Himalaya or Greater Himalaya. So again, confirming what we saw earlier with just the epsilon-Neodymium. We also looked at detrital zircon data. These are cumulative plots. So this is the age along here in cumulative probability. So if you get a very, very steep line coming up here, this sample has a lot of arc-aged grains. And if it comes off early, then it means we have more Indian plate grains. And the solid lines are from the peripheral fallen basin, and the dashed lines are from the downstream at Silliman and Kirta. And what you can see is that from the start of our samples in the Oligocene, unfortunately we didn't have any samples from the Eocene. You can see that already right from the beginning there's a difference in that we've got the peripheral fallen basins got an awful lot more of this arc material compared to the Silliman and Kirta downstream. And our fallen basin data are all similar. There's also published data from the Lower Kuldana Formation. That's the data of Kasim et al. 2008 and Ding et al. 2016. And these are the dashed lines. So we've added to our solid line data, we've added the Kuldana Formation data, but you can see they're very, very variable. They encompass all of the fallen basin data. Because they're so variable, averaging them is probably not the right thing to do. But what we can see anyway is that the zircon data back up and confirm our SMND data in that by Oligocene times, we've already got a difference. So we conclude that the Punjab tributaries joined the Indus drainage early. But why is this Marie Formation at Marie Hill Station, which is here, why is it different? Well, there's two reasons we could think of. If I take you over here to show you Marie in Marie samples in more detail. So this is the Marie, this purple is the Marie far to the north, north of Balakot at Paras over here. And you can still see this sample isn't anomalous. It still has lots of arc material. It looks like the rest of the fallen basin. But then all these other samples, which are from Balakot and they are from Muzaffarabad, and this is the data from Ding et al. 2018, they all have much, much less arc material. Now this could be because if you look in fact at the modern Jhelum River, they look rather like the Jhelum River. This is data from Alizé et al. And if you look at where the Jhelum River flows, it flows through Muzaffarabad. So maybe we're not looking at the Paleo-Indus here, and maybe it extended, maybe the drainage basin of the Jhelum River extended up to Balakot at that time before it did its U-turn. That's one idea. And that's also backed up by the fact that if you look at the Murray Formation at Murray Hill Station, it does look quite like the modern Jhelum River. However, we do also see an excursion to more Himalayan-like material in the Indus Fan and in fact in the Kirta ranges as well. This is a figure taken from Feng et al. 2021, and you can see, although it's not that clear, you can see in epsilon neodymium and also in strontium, you can see this slight excursion. And in fact, we do see this in Zhang et al. 2018 in the Kirta ranges. So maybe the Murray Formation, that excursion relates not to it being part of the Paleogellum, but a period of exhumation of the hinterland when more of the Himalaya was exhuming. And that does fit quite well with bedrock data. So if the Punjab tributaries joined the Indus early on, kind of close to Oligocene times, then we're back to the question of what caused the change at 6 million years. So Clift et al. 2019 proposed the change was due to more exhumation of the Lesser Himalaya, because as we talked about before, the Lesser Himalaya has very, very negative values, so it will bring the signature of the eroded sediment over here. Charouz et al. Proposed that they looked at decreasing proportions of 30 to 50 million year population in zircon fishing track ages, which they said was most likely from the Kohistan-Ladakh island arc. And this decreasing proportion of the 30 to 50 MA zircon fishing track ages since 12 million years, they suggested could indicate decreasing Kohistan-Ladakh island arc and increasing exhumation from the Himalaya and Karakoram, which would also end up pulling this signature down. But we wondered, could this difference actually be just, you've got progressive unroofing of the source region. If you unroof a source region through time, then you will bring younger and younger minerals to the surface. So we decided to use mica argon-argon dating because it has a similar closure temperature to zircon fission track, but white micas are nearly absent in the Kohistan-Ladakh island arc. So we could look at the parameters of other contributing sources with the Kohistan-Ladakh island arc removed. And then we wanted to see if the trend of decreasing 30 to 50 MA population could be replicated without having to invoke less or more Kohistan-Ladakh island arc. So we did the trital mica argon-argon ages. I've only shown you up to 50 million years. There are older grains as well. Depositional ages. These data, the references have fallen off, but these data here are published. This is the Camliel Formation, and this is published data from me, Najman et al. 2003. And this is Tata Modern River, which is from Clift et al. 2004. The modern Indus at Tata, ideally it would be better to have a modern Indus sample at the range front, but we don't have data from such a sample, unfortunately. But we think it's fairly representative because, in fact, the tributaries from the Beas and other tributaries that we've analysed, like the Kabul River, don't seem to have such young grains. So we do think that probably this is distinctive of the trunk river even further to the north. So we have two new samples here, and the reason I've put in this coloured bar is because unlike these, which have good magnetostratigraphic depositional ages, these don't. So I've put in the possible age range for this green sample, which is the Chinji Formation, and then the possible age span for the Nagri Formation. And what you can see is that exhumation increases sometime between the Nagri Formation and the modern river. Now, the way this works is this is the one-to-one line. This is what's called a lag time plot. So any minerals that lie on this line mean that the depositional age and the mica age are the same. So you've got 0 lag time. Now, the mica age is the age that you get in the source region, and then after it's cooled through its closure temperature in the source region, it's exhumed to surface, and then it's eroded and deposited. So if you've got very, very, very little time between the mineral age, the mica argon age, and the depositional age, that means you must have very rapid exhumation. And you can see in the Cambrial Formation time, still about 14 MA, you've got very rapid exhumation. But then by the time we've gone into Chinji and Nagri, we don't really have any grains that are on this one-to-one line. So we don't really have any more rapid exhumation. But then by the time we get to the modern river, we've got these young grains again. So not very many, but we've got a couple. So that suggests that sometime between the Nagri and the Tata, we've got the onset of rapid exhumation. And these grains are most likely from the Lesser Himalaya, although the Lesser Himalaya are the old grains, which I haven't shown, or the crystalline Lesser Himalaya, or the Karakoram. The Indian plate itself mostly had a period of rapid exhumation till about 18 million years, and then it hasn't had, apart from the Nanga Parbat region, hasn't had much rapid exhumation since then. But we wanted to see about the proportion of grains that are 30 to 50 million years old and see if they decrease progressively, and therefore we can talk about the trend that Chirou's got without even invoking differences in input from the Kohistan-Ladakh island arc. So this is the more than 50 MA proportion of grains, and in black we have the 30 to 50 MA proportion of grains. Again, Marie Hill Station, we're going to leave that out because it's as I showed, it's a very different signature. And what you can see is, again, we do have this decreasing proportion of this 30 to 50 MA population within the same time range that Chirou's et al. Analysed. So it seems to us that probably this increase of young grains through time is due to or can be explained at least by progressive exhumation of one source. So then we know we have rapid exhumation sometime between the Nagri Formation and the modern day, which fits in with the timing of the change in the Indus Fan at 6 million years. What could it be? Well, if we look at the zircons again, and this is the Nagri Formation, which is mid-Miocene, and this is the modern day in red at Attock and the modern river at Tata. And what you can see is we've got quite a high proportion of grains at 1,800 MA, which is absolutely typical of the Lesser Himalaya. So we've got quite a big input of Lesser Himalayan material in the modern day, but we really don't have that much in the mid-Miocene Nagri Formation. So this suggests to us that the change in the geochemical signal that we see is probably due to increased exhumation of the Lesser Himalaya. So to conclude, we think the lower Indus drainage was stable since Oligocene times, which agrees more with Chirou's rather than Peter Clift. And the change at 6 MA was the result of increasing exhumation from the Lesser Himalaya, which fits very well with the new paper from Clift et al. 2019. So thank you very much. And shall I stop sharing screen?
Yes, please stop sharing screen and we will take questions.
So thank you very much, Yani, for a very interesting talk using a lot of different techniques to look at the history of these sediments coming off of the Himalayas. Curious, just to start off the questions, I'm curious about the sands in the modern rivers. And if I'm not mistaken, in your next to last slide, or your third from last slide, you showed quite a difference between the river at Attock and the river at, was it Tata?
Tata, yeah.
Uh-huh.
And
Yeah.
and is that's because of the contribution of the Punjab tributaries?
Yeah. That's because, oh, I'm not sharing screen anymore, but yeah, the modern Indus at Attock has got a very high proportion of arc-age grains, and the modern Indus at Tata has a much lower proportion, just because you've diluted it with all the Punjab material coming in from the Indian plate.
Right.
Okay.
That's a remarkable observation, and I'd be interested to actually take that back into time, because in the Siwaliks that we've studied in the Patwar Plateau, there are some rivers that we believe are, or some sandstones we believe were deposited by the ancestral Indus River, and then there's some sandstones that were probably deposited by the ancestral Jhelum River, just for example, in the upper part of the Siwalik package. And it'd be interesting to tease those apart based on detrital zircon dates.
Mm-hmm. Yeah, I mean, I've done a little of that in the Camlial formation, in that I've got a whole load of samples that mostly show one type of sample, and then you've got one type of signal, and then you've got a different signal, which I think is, yeah, I would say is local. I don't know if it's palaeo-Jhelum, but certainly Indian plate, and there's not much arc material coming in there. I'm just doing a close to submitting a paper on this, actually, where we're going to be able to have published this data and hopefully get it out to everybody soon. I should be in the next few days. I've been saying that for the past few weeks, but in the next few days, I hope it should be ready to submit. Because you can see, if you go to the Camlial, I wonder if I can, let me see if I can share screen, and if I can go back to the slide I want. Yeah, let me.
While you're digging through the slide stack, I just want to mention that the Siwalik sediments are extraordinarily well calibrated by time, and of course are readily available for sampling, versus the Indus cone, which is a little bit more, more logistically challenging to get into. So it'd be fascinating to leverage your studies into the stack of there's 3 to 5 kilometers of sediment in the Siwaliks, and it'd be wonderful to compare your observations to the simple petrographic observations that we've made in the past, for example, the presence or absence of green hornblende, or even just the physical color of the sandstones, because Kay, who's on the call, and Catherine Badgley, who's also with us, noticed this over in the core area, and we saw it in the eastern Patwar. There's some very distinctive macroscopic characteristics of sandstone beds, color, bed form, and paleocurrent direction that could be, identifying different river systems, and it'd be interesting to tag them with their detrital zircon suites.
Yeah, I mean, we've only got in detail detrital. Can you see my screen now?
Not yet, no.
Not yet.
Why not? Hold on, I'll try again. I thought I was sharing screen. Okay, let's try that.
Yeah, now it's coming.
Now
coming.
it's good.
Yeah, it's coming.
Yeah.
We see it.
So we've obviously only done detailed sampling from the cambrial. We've got a little bit in the Chinji and a little bit on the Nagri, although we've got more samples than that. And you can see that there is definitely a difference. We've got a whole pile of young grains. And then because I chopped this off at 50 million years, you can't actually see the sample I want to show you. But there's another sample that is basically all old grains. There's not a single Himalayan grain in there. So that suggests to me that we've got some interfingering. It was just one sample, but we've got some interfingering of major rivers and ones with a totally different source. Now, to tell whether you've got a paleogellum or a paleo-Indus, it's best not to use micas. It's best to use zircons. And, you know, it'd be lovely to do the whole lot. That would be another interesting paper, actually, to do the whole lot with zircons. And it should be very, very easy to tell the gellum or to tell local sources from the Indus.
Right, and I would tag it back to the modern, because again, your slide that had the Tata sample, again, now we've left, but the you know, there's clearly you could go to the Jhelum River today and get samples out of the Jhelum River at the town of Jhelum, for example, and you could compare those to samples from Attock, and then actually Attock, you're commingling the Kabul River, so it'd be interesting to sample the Indus River up at Tarbela, for example, north of the Kabul River.
Yeah, I mean, there's a paper by Alizé, which is one of Peter Clift's colleagues, that has done a lot of that. There's a whole paper on Alizé 2011, a whole lot of data on uranium-lead zircons of the various different rivers. What is sorely lacking, what I would really love, and is we wanted to do maybe, yeah, indeed at Tarbela. So we've only got Attock, we've got some micas, but it would be great to do at the range front SMND and UPB, because Charouz had to use samples from further up, which in fact were before they come through the Greater Himalaya and the Lesser Himalaya. And so it's not a completely accurate comparison. So, yeah, I mean, I was thinking for this paper, should I try and see if we can get some samples? And I just thought, you know, by the time we've got the samples and then we're in lockdown and then we try and analyze them in a lab that's shut for 6 months, you know, we just have to go with what we've got.
Yeah.
So
we have some couple of questions from first of all Rajiv Patnaik. Please open up your mic and ask.
Hello, Dr. Najman. Can you hear me?
yes, I can. Thank you.
Yeah. Thank you so much for it. Was a very nice talk.
Thank
I
you.
really enjoyed it. My question is, you mentioned that in the Lesser Himalayas, almost entire Oligocene is gone. I mean, there is a big unconformity. You mentioned that you don't find deposits belonging to that period. But we do have some of such sediments exposed in the Bukti area. Could you please, could you please tell us something more about this?
About the Bukti area.
No, why?
Oh.
Why? Why such a difference?
Well, that's a good question. So let's assume that. So Bukti is that in more so like the lower Indus Basin?
Towards. Yeah, please.
Yes, it's in the Nari formation is Oligocene, and it's from the Hosdar area up to Karachi area. So it's in the lower Indus Basin, which
so
is specific.
Geologically in the lower Indus Basin. Yeah.
So I suppose the question is then, why, if we accept that there's an unconformity basin-wide in the peripheral fallen basin, but it doesn't seem to be in the lower Indus Basin, which I agree with, why is that? So there's been maybe 4 or 5 papers that have come up with different reasons for the unconformity in the peripheral fallen basin. You've got Descelles et al., who I think it's 1998, who maintain that it's due to the movement of the peripheral forebulge. You've got loading, and then when the mountain belt loads, then you've got a peripheral forebulge in the basin, and then as the mountain belt progresses, the peripheral forebulge moves. So that's one idea for why it's formed. Then there's the French group. I've forgotten the name of the first author. It's a paper in geology, and one of the authors is Peter van de Beek. And they say that they think it's more, I might be misquoting them, so I haven't looked at this paper for ages, but I think they want a sort of a larger uplift and something to do with mantle processes. Then you've got Peter Clift, who I think wanted a redistribution of the load to be climate related. So there's quite a lot of different viewpoints as to how this peripheral forebulge formed. How this unconformity in the peripheral fallen basin formed, which you don't see further to the south. And there are some people that think that there isn't an unconformity in the peripheral fallen basin. There's a paper by Berra, who believes that, I think that it's more continuous than than a lot of us would believe.
Right. Thank you. Thank you very much.
Catherine? Yeah.
Okay, very good. Thank you for a very interesting talk, Yani. I had a question about the current directions that I think Bob alluded to. You know, we have sedimentologists who've taken current directions on some of the big rivers in the Kamloops and the Chinji and the Nagri formations, and the major current directions are going to the southeast, unlike the direction of the tributaries in the Punjab in Pakistan today. And I'm just wondering how one could reconcile that observation, which seems based on, you know, at this point, hundreds of current directions, with the interpretations that you've presented. So I'm curious how all of those can be fit into one model.
I'm not sure how they can. I mean, there's a paper by Burbank, it's at 1996, in that big book that summarizes the paleocurrents of the fallen basin.
Okay.
I mean, you'd have to have it. I mean, the Indus Fan is definitely, if you believe Peter Clift, which I kind of do, the Indus Fan has definitely been on the go since the Eocene. So you're going to have a major river coming down that way for since that time. We could, I suppose, say that it diverted to the east for a while and then came back. That would work. But to my knowledge, there's a fairly continuous record in that Indus Fan. So then I'm thinking, well, could it be that they're going to the east, but they're part of a switching larger system that is coming back and eventually still lands? Because I think I don't know about this. If it went to the east for a while and then came back, then I should see a larger proportion of arc-aged grains in the Bengal Fan during that period. And there's a paper we wrote, Blum et al. 2018. And we don't see that spike in arc-aged grains. Now, I suppose one could argue, but that by the time it had travelled all the way to the Bengal Fan, maybe such a contribution would be heavily diluted. But this was a great advantage of the system we used. We analysed at the Arizona Lasercon facility, and they have rapid throughput, and we analysed more grains than I could ever imagine. So, you know, normally if you've got n equals 100, you think, well, you know, you could have missed them. But actually, we had grains popping, we had data popping out of our ears. It was incredible. So we will be doing more on that. We've got an NSF NERC funded project on hold at the moment, courtesy of COVID. But we are looking in more detail, and we're going to be doing even more work on the Bengal Fan and zapping even more zircons. But,
so just one last just one other idea that I can throw out is I'm wondering if the Indus has been in its stable sort of major drainage position the way you've presented, but that at least one of those Jhelum tributaries was a river capture at some point, a late river capture, maybe after 6 million years ago. And one thing that a paleontological observation that's interesting is that the fish faunas, which are prevalent throughout at least the Camliol through Dokpatan formations, are more similar to the modern fish faunas of the Ganges than they are of the Indus. And that's across several different major families. So that's an interesting observation too, that shows that at least something contributing to the Siwaliks seems to have been allied with the Ganges system, at least through the Dokpatan formation. Now, we don't have enough data from our own group to say anything about what happens younger than that, but it just presents an interesting pattern that we will eventually need to reconcile with your, otherwise very convincing analysis.
Yeah, I mean, I don't have any data from the Dokpatan. Which is disappointing, although I do wonder if even if I did, if it would show anything, because I wonder if, I mean, I don't know, but by the time we get to the Dokpatan, is it mostly more local sourcing?
That's what we're thinking. Yeah.
Yeah.
It's more what we think is draining the foothills.
Yeah.
At least, although early in the Dokpatan, there's an interfingering of the Nagri sands with the smaller scale channels of what we call our Buff River system, which Kay thinks is draining the foothills. So, and then gradually the Nagri sands become less prevalent, and it's mostly the foothill dominated sources.
Yeah, that's what we see over in India and Nepal as well. I mean, there must be the Paleo-Indus hanging around there somewhere, but that's kind of put me off analysing them a bit, because it's like, well, am I just going to see local stuff? So, and I haven't got any sample anyway, so the the opportunity wasn't there. So maybe I should. Maybe, I mean, I'd certainly, I would like to. So I've got a lot of samples from the Camliol, and then I know that magstrat goes up into the Chinji and Nagri, and I think back in the UK, I can't remember whose magstrat that was anymore, but I remember the person sent me the sample locations, and then it didn't seem the right time to be working in Pakistan. But I think I've got unfinished business there. I'd definitely like to go and do like what we did with the Camliol and get loads of samples and look at changes up section. That would be great.
Yes, it would.
So, and maybe the time is coming after COVID.
I hope so.
Yeah.
Thank you.
So we have Professor Kasimjan. It's your turn, sir, for a question.
Thank you. Very nice presentation, Yani. My compliments.
Thank you.
I'm wondering whether the sediments in the Makran accretionary prism have provenance in the Himalaya, or have they been drained from Kabul block and Lat block in Iran? Because we are composing a paper currently, and I have a difference with my colleagues. Some of my colleagues have suggested that the sediments are from Himalaya brought by the Indus River system. And I am wondering if the Indus River system sediments spread that far west to Makran coast.
I think it's very, very hard to tell. I mean, I was a co-author on a paper with Andy Carter, geology, some years ago, where we maintained that we thought that there was that the Makran was looked very Himalayan, but I was very, very aware that our source characterization was poor. Again, what we need is samples from Afghanistan, and I really tried. I was so close. I had a friend who was in the military out there, and I'd got him all sorted to go and get some modern river sands, and then it didn't work out. So, you know, without knowing what that upstream source in Afghanistan really looks like, it's really hard to tell. And then I was on the PhD committee of, I think his name was, I'm going to say Muhammad Ali, the student of Jean-Pierre Berg at ETH in Switzerland, I think. And they have the most
That's probably
is that the right?
Yeah, he's an Iranian, I think.
Oh, Iranian.
Yeah.
Okay, all right.
Iranian, yes.
And they came up with the idea that they thought that there was much more sourcing locally rather than from the Himalayas. And, you know, I have to say that really with that unknown of what the source would look like, and maybe we'd be disappointed even if we did have the source. Maybe the source characterization would be so similar to the Himalayas that we still wouldn't be able to tell. But it would be nice to know one way or the other. So to answer your question, I don't know.
Thank you. Thank you.
Any chance of getting samples from Afghanistan anytime soon? That would be.
Well, if you tell me the locations, I can grow beard and join the Taliban's.
I have all the sample locations ready and waiting. I have GPSs, I have Google Earth, but then it didn't happen.
We can talk about it some other time. I think we can communicate and see if we can collect the samples from Afghanistan. It shouldn't be impossible.
Yes.
Yeah. Is it safe?
Yeah.
Well, somebody will do the job for us. There are some of them. No?
Yeah, I know, but I kind of don't feel it's the right thing to do to ask somebody to do something that I wouldn't. I don't know.
Well, unfortunately, at the moment, Afghanistan is in a great uncertainty, and we don't know what will be the situation in another 6 months' time, let alone a year. Yeah.
I'll send you the sample coordinates, and then if you get an opportunity, be safe, but.
Thank you.
We have a question from Adnan Khalid, so you can unmute your mic and go on, please.
Hello, madam. Can you hear me?
Yes, I can. Thank you.
Okay. I would like to extend this question of Dr. Qasim Jan sir from that. What is the source of sediment in Tata? Maybe I skipped it, or maybe I missed out. But what do you think? What is the source of sediments? It's from Himalayas, or it is from the Siwaliks from the same region? Because we have a very thick sequence of Siwaliks in Karachi 4 Park and Kirtar 4D.
Sorry, I didn't catch which area you were asking about. You were asking about the lower Indus Basin?
Yes, the Tata river which you sent.
I would assume, I mean, we've done some analyses in Kirtar. There's a paper by Zhang et al., EPSL 2018. And to us, they look very Himalayan-like. Also, they show that pulse in the Marie Formation that also we see upstream in the peripheral Foreland Basin, and we see downstream in the Indus Fan. And if you see that same pulse in three places, that kind of suggests to me that they've probably got the same drainage. So I would go for Himalayan for that. But I'm open to other options.
Okay. Okay.
Would you
All right.
agree or not?
Actually, because it's very close to this place, there is a very thick sequence of like Manchar formation, which is now equivalent to Nagri formation. It's in Karachi arc. There's a very thick sequence over here and in the Kirtar 4 deep also. But Kirtar 4 deep is far away from that place, around 140 kilometers. So this place is very close to it. That was the thing. But maybe your sample analysis can say anything about this nature or no?
About the
Nature of the sediments, the zircon or whatever the analysis which you made. Yeah.
Yeah, so they look like they're a mix of we don't have any data from
the Tata River, which you already mentioned.
Yeah, so that's the modern day Tata or the ancient Tata?
Like it should be the same almost, but it should have the deposits of sediments.
I think it's a mix of Karakoram and Kohistan, the Dak Island Arc, and also Indian plate. So, but not with the Lesser Himalaya until, well, about 11 million years. It seems like the Beas and the Sutlej. So we're doing a paper on the Siwaliks in that area in northwest India at the moment, with the uranium-lead zircons there, and that seems to be roughly similar to what my previous paper suggested, that we've got Lesser Himalayan input from 11 million years. So I would think that the modern and the ancient won't look exactly the same, depending how far back you go. But I think the Karakoram and the Arc and the Indian plate will be there from the beginning. So
because this leads to a very basic question that is there any shift in the drainage over here or no in the Tata region? Because we normally read that post-Oligocene was a major episode of folding and like there was a big shift in the tectonics. So there was a change as well or no?
I'll hopefully be able to answer that in maybe a few months. We've got data from the Katawas Basin, and some people think that the Katawas Basin was where the Indus flowed. Some people think there were two Indus fans, kind of like two fans. Some people just think that it was in the Katawas and then shifted east. We haven't really started interpreting that data to any great extent yet, but yeah, give me a few more months and well, maybe a couple months is a bit optimistic. Maybe give me 6 months and then we'll have looked at the Katawas data more. And if we see an Indus signature in the Katawas and in the Kirta and Suleiman ranges, I'm not sure how I'll interpret that yet. Guess I'll cross that bridge when I come to it. So I'm check back with me in a little bit.
Yeah, sure. Thank you very much.
So I think that's pretty much it, Bob and Yani. We don't have any more questions. So yeah.
Let me maybe wrap up a little bit here. I think the challenge that we are facing is a better understanding of literally the mineral grain compositions of these sandstone packages, because we have seen in our studies of the Siwaliks the heavy minerals changing, which we can see petrographically. The presence of, for example, the green hornblende is a very distinctive component, and there would be others. And there are studies like that that have been done in India as well. And I think that we're standing at the cusp of a new understanding, because we can take the heavy mineral compositions and detrital zircon age spectra we can, use these tools in concert or together to better understand this differentiation. And you've shown that there's a clear difference between the materials that are coming from the arc versus the old Indian plate. And so there's clearly an opportunity to sort that out. And I'm eager, Yani, to hear your results as the months go forward. And I'd like to maybe end with that optimistic looking to the future, where we can maybe use some students from Pakistan and the subcontinent to work on some of these projects. And certainly there's a lot of labor involved in sorting the samples and analyzing the data, and it might be a fruitful opportunity for some of the people who are listening from the subcontinent to calibrate some of these sediments in this new way. But I'd like to thank everybody for participating this morning and this evening, and I'm looking forward to our talk next week, which will be about the paleontology of the Upper Siwaliks. And I thank you all for your attendance and look forward to seeing you soon. So
thank you very much for inviting me.
Thank you very much.
Thank you.
Thank you all very much. Thank you.
Good night and good morning.
and Peter Melenge, we'll see you soon.
Indeed. Inshallah.
Inshallah, yes.